Hi, good afternoon, everyone, and welcome to this session on Dockers and containers. Um, my name is Srikanth. I work for Radiology Informatics at Philips. So basically, this is a session about basics or fundamentals on Dockers and containers. So in case if you already have worked with containers and you know what it is, probably this session is not for you. If you haven't heard about Dockers or you were curious to know about it, probably this is the right place. Okay, let me just begin by saying like I'm going to cover only the fundamentals here, so don't expect that I give you elaborate demos. Basically, I'm trying to get your basics right so that you understand the internals of Docker and how it works. And there's plenty of material on the net, so you can find and progress yourself once you have these building blocks rightly set. Okay, let's begin. So before I begin, I just want to walk you through um, just how it all began. So if you look at the computing evolution, right, so it started in the 1970s. We have the mainframes, and it's still there today. In fact, most of your railway reservations and then your bookings all happens on mainframes. Those are big beastly machines, and then they're very stable, and of course are also constrained by their physical location. So mostly you're going to work with the terminals attached to that, or probably in a nearby place, or in a dedicated network. So it's not really open for internet, at least not for in usage in this internet era where we use it for the WWW, the World Wide Web. So it's mostly used for as a single system, a monolithic system, and you need it to be there near the system, need to know the internals or the programming languages used on the mainframe. You need to know, you need to be a tech savvy person to use mainframes. That's what it was in 1970s. And in the 1980s, this is actually what opened up computers to really the general public. So it started with microprocessors. I'm sure many of you would have heard about 8085, 8086, and then all the x86 machines. And then it progressed well, and then there was advent of IBM computers, which is basically what we know as the modern day desktops. So 1990s was dominated with desktops with a screen, a monitor, and a keyboard, mouse, a CPU unit sitting next to it, and that's how I think we all began our careers looking at computers. And in the 2000s, basically virtualization came into picture. So you could make better use of desktops or your hardware by partitioning it virtually. I mean, you can actually run many virtual machines on single desktop, and you can actually create a farm and use it to compartmentalize all your software with different, maybe for your database or UI or many more what you want to do. You have multiple options on multiple virtual machines sharing the same hardware. And of course, in 2010, it was the beginning of the era of containers. There was a company which was created by Solomon Hykes. It was known as dot uh, dot source, I think, um, which was later renamed as Docker. And right now, Docker is an open source backed by many of the biggies like Cisco, Google, IBM, etc. And then recently, I heard that a company called Mirantis acquired Docker and in a bid to keep the Docker system alive with basically offering Docker as a service. So right now, Docker is one of the hottest topics around. So you get plenty of material to know what is Docker and then how it works. So this session is actually aimed at somebody who actually knows how virtual machines work. So if you actually know how a virtual machine work, I'm going to use that as a prerequisite to actually walk you over to the next logical step of basically moving into containers. So before we actually go take a deep dive into Dockers, I want to make you mm, understand or probably refresh your understanding on what is virtualization. It is very important that you actually look at this video and then focus on every aspect what they're going to talk about in this video. This is actually from VMware explaining the benefits of virtualization. So this is a little older video, and if you actually relate the same video now with the Docker in context, you actually see all of these benefits. What you actually see for virtualization gets actually amplified, or basically you get more of what is being said there by Docker. So Docker basically takes the virtualization concept to the next level. So just um, observe each of these benefits what you see in this video. We're going to probably talk back and refer to this as we move along.
Traditional server architecture consists of one operating system per physical server and one application per operating system. With VMware virtualization, a hypervisor is installed on the physical server to allow for multiple, unique, and isolated virtual machines to run on the same physical server. Once we've separated the operating system from the hardware, we can utilize the hypervisor to present a complete virtual x86 platform to many virtual machines. vSphere Hypervisor is the free version of VMware's leading class architecture that helps you save money through consolidation, get up and running in minutes, utilize an extremely thin architecture, requiring only 144 megabytes of space to install. A small disk footprint means reduced attack surface and fewer patches. VMware Hypervisor features superior scalability and manageability, is easy to install and use, and can be upgraded just by changing the license key. Some of the key properties of virtual machines are partitioning, running multiple machines on the same hardware and sharing resources between them; isolation, fault and security isolation at the hardware level; encapsulation. The entire virtual machine can be saved to files and moved, copied, backed up, and restored. Hardware independence. The virtual machines are not tied to specific hardware or vendors. So, what's the problem that we're trying to solve? IT has the constant pressure to reduce costs while providing more. The core benefits of virtualization include reducing complexity, dramatically lowering costs, and enabling a flexible, agile IT service delivery. How does this happen? By consolidating many existing servers onto a fewer number of servers, by containing new applications through virtualization and managing the growth of existing ones, and by increasing application availability and data recoverability. We can even save time during disaster recovery. In the physical world, server hardware had to be reconfigured, the OS installed and configured, and the backup agent installed before we could even start the recovery process. When virtualized, a simple restore of the virtual machine files and a power on is all the time you need. This allows us to eliminate recovery steps and standardize the recovery process no matter what the operating system. With a technology called thin provisioning, storage space is much better utilized. The virtual machine will only utilize space required on disk for what is utilized inside the guest operating system. It's also very easy to convert virtual machines between thick and thin format. You can make better use of existing infrastructure. In this quick example, 10 physical servers are reduced to only 3 physical servers. This represents a very conservative consolidation ratio of about 3 to 1, and ratios around 8 or 10 to 1 are typical. CapEx savings are just the beginning of the story.
What are containers? Well, I mean, if you want to understand Docker, Docker is actually a type of container. So basically, Docker is just one type of container where there are other containers like Linux container, Apache Mesos, Flux, etc. We're not going to go into the details of all the different types of containers, but if you actually look at what is a container, we need to first understand how the software layers are organized in a computer. So at the onset, you actually have a computer, which is basically hardware, basically bare bone hardware on which you actually install the OS. So what is the OS? Basically, it starts with your kernel, drivers, the hardware abstraction layer, which is all part of the operating system. So in this case, if you're talking about Windows, it's all about the Windows drivers. On top of it, you also have a lot of APIs, basically Win32 libraries, which interface between the kernels and then the application. So basically, if you want to access any hardware, you need to go through the kernel. And then there are basically two different types of user space here. I mean, two different types of partitioning, which is basically the kernel space and the user space. So if you actually want to access the kernel space, you need to have system admin privileges, the highest privileges to access, and the no other component can actually bypass this and access the hardware. So it's completely abstracted. On top of it, it actually the user Win32 libraries or the Windows operating system itself, components itself sit, and then which interface with all your applications, including the operating system applications. When you install an operating system, obviously you get a lot of OS apps, which is basically the features of the operating system itself. For example, PowerShell, IAS, your command line interface are all built in. I mean, many of them are enabled by default, so they are actually part of the operating system itself. And just like the operating system applications, you start build your own applications. Building your own applications, it could be your custom application, even the .NET Core, the GRE, MongoDB, MSSQL, etc. So now going into these compartments, what containers have done is basically um, taken the topmost portion here. So if you actually take out all the software layers, which is except for the kernel here, you actually get all your applications, the OS applications, and the OS itself, basically all the Win32 libraries, except for the kernel, the drivers, and then the hardware related stuff. You get all of this. So if you actually package this in, let's say, a zip file, in the Docker parlance, it's actually a tar file. So if you actually package this, that's called an image. So that's what actually gives you a container. So container is like basically a package which actually can run on its own space. So what happens when you actually package? So you can create an image of an app, OS apps, and then the related libs. The biggest advantage with this packaging is that there is no longer the dependency management headache, which you will probably have if you actually separately distribute your application. Let's say, for example, you have a .NET application, and then you create your custom application using one version of .NET, and then there is one more or some other third party which probably uses .NET Core. So then you need to ensure that these two actually can coexist. So they need to be tested together. You need to verify that they can work along, and then there's no problem with the libraries being no, the shared libraries eating or stepping on each other's food, etc. So basically, how do you resolve that problem? If you package all that together, including your operating system libraries, which includes all your applications, including your .NET layer, you're going to solve that problem. So with that, we can actually create more and more containers. So you have Nginx, let's say a MongoDB image, an IAS image, etc. I know what's your next logical question. So basically, if you actually start creating one application after another just by simply duplicating the whole OS, isn't it going to be expensive in terms of the space consumed? Well, Docker actually has an answer for that, and that's how Docker actually provides you value. It actually does not really duplicate all the entire OS libraries. It has a concept of layered file system, so it combines all the OS apps and libs together and starts just using the layers which need to be on top. So only the top layer is different. So it uses a layered file system. So if you actually see a container has image 1.0 to start with, and you add Apache to that, and it's called 1.1. now, and then you add some more to that. It becomes now you're adding Git. So it has image, now becomes image 1.2, and on top of it, you actually add something more. So basically, you actually start adding each layer after layer. So it uses something called union file system. So what is a union file system? Basically, the underlying layers actually become read-only, and then what you see is actually a union of all these layers. So for a given application, it actually is a complete file system. Whereas if you actually look underneath, only the top layer is like something which is like a diff file, which gives you a difference between what's there and what's visible to the application and what lies in underneath. So you actually get like a sum up of all the information or the content which forms the basis for this file system. So if you actually go back to your machine virtualization, right? So you have the hardware infrastructure, you have the hypervisor, which is sitting on top of it, and then of course all your guest OS, which sits on top of the hypervisor. And on in each of these guest OS, which is completely isolated, you have your own binaries, including the libraries supplied by the OS, plus all the libraries of the application, etc. So similarly, if you actually look at in a Docker world, you have the infrastructure at the bottom layer, and then on top of it, you have the operating system setting. It could be your Windows 10 or your Windows Server, so both of which now support Docker natively. And then container engine, which actually is your virtualized hypervisor kind of layer, which actually gives you isolation between the operating system and your applications itself. So on top of the Docker engine is where your complete libraries of the OS, the bins of your application, everything sits here. And then the container completely abstracts the operating system. So for each of these application thinks that uh, it actually gets the entire operating system to itself. So this forms the basis of containers. So let's now look at a demo of how actually things work. And then while we go along with the demo, we can actually delve into a little bit of more details on understanding how this actually works. So as I already mentioned, basically containers are nothing but images. So images is nothing but a zip file or compressed file format. Actually, in a Docker, it's a tar system. It's a Unix based zip file. So, and that tar file is the image which actually is uploaded onto your Docker Hub. Again, what is Docker Hub? Docker Hub is a repository just like your App Store. So it can store all the images. So you once you create an image, you can actually upload that image back into the Docker Hub, and whoever wants it can actually pull that image and starts working in an instant. So we can see how quickly we can actually pull down a container and start it using just a Docker command and start using it right away. So let's look into the demo next.